So we have our next presenter, Dr. Issa Dahabreh, and he's an associate professor of epidemiology and biostatistics at the Harvard Chan School of Public Health. And his research work focuses on causal inference methods and specifically on combining information from observational and experimental studies. He also worked on evidence synthesis methods and applications for treatment, medical tests, and predictive models. So Issa, we're very excited to have you. So if you can share your slides.
Sure. Thank you for having me. Thank you for the kind introduction. Let me see if I got this right. Yes?
That's
Okay.
nice. Yeah.
So I'm Issa. I'm going to talk a little bit about some ideas we have for augmenting clinical trials with external data. But I find increasingly I don't enjoy talking only for specific technical things. And so I thought I'll frame this as an instantiation of a specific framework for causal questions. So if you'll allow me, I'll use a few minutes to discuss a general approach for answering causal questions. And as I was preparing my slides, I thought this high-powered group, I had been prepared for this intense audience. So I thought maybe I can set myself a bigger challenge and say, is there a general approach for answering all empirical questions, not just causal? And then Dan is super strict, tough audience. So I thought maybe I can go bigger. And so I'm going to do a general approach for answering all practical questions in life. And here it goes. It's very simple, really. First, you ask, what do I want? Then you say, what do I have at my disposal to get that thing done? And then you decide what to do in view of what you want and what you have at your disposal. And I wish this was my idea. I would write a book and become a pop lecturer. But for me, credit goes to a high school math teacher who, in Greek, because this is where I did my high school training, repeated a rhyming phrase in Greek that says exactly this. What do I want? What do I have? What do I do? Greek is a superior language, so the actual words rhyme, but we will do what we can. And again, you know, I wish my teacher was the first one, but probably the ancients had the same algorithm when solving theoretical or engineering problems. And of course, you know, this is data science, causal inference. We don't like simple things, so we have to elaborate a little bit on the framework. And so as a general data science structure, maybe what this translates into is we have a research question, and then the things that we work with are really assumptions and data sources. And what we do is we use some kind of study design. And here I'm going to talk mostly about using existing routinely collected data, because this is the space where I do most of my work. And so when I say study design, I don't necessarily mean going out and collecting new data among newly sampled people, but also gathering existing data resources and organizing them in a way that makes the assumptions more plausible and allows answering the research question. And then we do some data analysis and we interpret our results. Now, I come from the causal inference world, so we like even fancier terminology. And so, sorry, wrong way. And so what you get is you get basically fancier terms for the same ideas. So always you start with a research question, you convert it or you map it into a causal quantity that maybe we call a causal estimate. And then we obviously need models and assumptions, and the assumptions tend to come in three flavors: causal ones, sampling ones, statistical ones, and then we get data for our analysis. And the activities that we do are pretty much analysis and interpretation, maybe with some sensitivity analysis thrown in, because our causal assumptions are often speculative or uncertain or even controversial. And then there's this interesting step where we have to translate the causal estimate into a statistical quantity so that we can go and use the tools of statistics. And that goes by the name of identification. So basically, it's a mapping or a rewriting, if you will, under our assumptions of the causal estimate into a statistical quantity, a quantity that involves the observed data, and then we go and estimate that. Now, first of all, obviously, this is not my idea. Many people in econometrics, biostatistics, epidemiology have thought about similar structures. To some people, some version of this will be familiar as the causal roadmap. That's totally fine by me. And so it is what we have. Of course, I also presented a little in a simplified way. It looks a little too linear. In reality, this is an iterative process. And of course, anything I write on a slide is going to be an incomplete representation of something that's messier and perhaps to many of us very enjoyable in using data to answer questions. And so with this framework in mind, I'm essentially going to go over each of these steps, but try to now apply it to a specific kind of research endeavor, which will be taking a clinical trial and trying to do a little better by using external data. And the notion of better that I have in mind will become clear in a second. Okay, so my causal question, I'm not going to spend too much time here because basically I inherit that from the trial, right? If you took the time to design the trial, if you have a protocol, then you have a well-specified causal question in your mind. And so I'm just going to inherit that and try to work together to make it, to try to do a little better by using the external data. Now, here is my rough sketch of a study design. So you have the trial, and I'm going to talk about it as if it compares an experimental treatment versus control. This is just language. It could be two active treatments. It could be two different doses of the same treatment. But just for convenience, it helps to be able to say the treatment and the control. But then what you have in addition to the trial in my setup is going to be a large supply of external data on the control strategy, which I will assume has been collected separately from the trial and possibly in a different population. One way to think about this is perhaps you have a clinical trial, perhaps you have access to a very large electronic health record, or perhaps you have historical data from previously done for a moment, let's say single arm studies. And so you have your A versus B trial and you have a lot of B type data from other sources. Can you do anything with that? Now, when we are combining data, we need some kind of sampling model that will allow us to put all the data sources together. And so I'm going to work here under the assumption that the data from the trial and the external source are obtained separately, as I said, possibly from different underlying populations. But my interest throughout this talk is going to be on the target population represented by the trial. And in some prior work, we've called these kinds of designs non-nested. Roughly speaking, you can think of them as stratified random sampling, where the stratification is by participation status. And I'm going to treat it as if the trial and the external data are simple random samples from some respective underlying populations with unknown sampling fractions. Now, I need to say two things about this here. The first, why do I treat the sampling fractions as unknown and actually unidentifiable from the data? In my view, in many reasonable applications of this methodology, there is no a priori planning for a joint analysis of the trial and the external data. And so the sample sizes of the two datasets usually do not reflect anything about some real underlying population. In particular, the relative sample size then does not reflect the ratio of the proportions of these two sources in any kind of reasonable population. And so from this, one way to think about it is these are separate, but I'm not going to think that their relative sample size is somehow anchored to something real. And that's fine because my target population is the one underlying the trial. The second thing I think I need to defend a little bit the modeling as if the data are simple random samples. And so I'll say many analysis of trials, many straightforward analysis of trials, use large sample methods that in their underpinnings have these kinds of IID, large sample, kind of superpopulation models. And so here you can think that I'm not doing anything different, except I'm doing this twice. I'm doing it for the trial, and I'm doing it for the external historical data. Could this be improved, perhaps by doing a better job at finding the trial population? Of course. Could this be improved by having less reliance on large sample ideas? I'm pretty sure that's the case, but we have to walk before we can run. And so I'm going to do the basic case, basically extending typical assumptions made in the analysis of trials to the two dataset case. With this, let me introduce a little bit of notation. And I present this notation with a work with me principle kind of attitude. This will become clear in a second. So I'm going to use capital X italic for baseline covariates. I'm going to use S as an indicator for the data source. And so S1 will indicate the trial, S0 will indicate the external data. I'm going to use capital A for the treatment assignment. And this is where the work with me first step comes into play, because I'm going to assume that there is no non-adherence. And so treatment assignment is equivalent to treatment receipt. You could think of this as applying to a trial where everything is super adherent. Another way to think about it is that this is a simplification, work with me, that I'm making just for this talk. The methods we will come up with together, you'll see very clearly can be extended to be combined with methods for non-adherence, for instance, for the estimation of per protocol effects. But I find, in a Zoom presentation especially, it's a little too hard to do too many things at once. So we'll do the simple problem, perhaps a little unrealistic. And then, if there's questions, I'm happy to expand a little bit on how non-adherence could be addressed. Similarly, I'm going to have an outcome that I treat as cross-sectionally available at the end of the study without censoring, without missing data. Is this realistic? Perhaps in small, short follow-up trials that are done really well, it can happen, but in many long-term follow-up studies, there will be some censoring, some missing data, many complications. Again, work with me principle. The usual methods, let's say inverse probability of censoring weighting, could be applied with the methods we're going to develop together. But again, I don't want to do too many things in one go. Okay, so with these simplifications, here is what the data structure looks for the kind of design that I described. So first of all, from all the observations in your data set, you have your covariates X. Then for every observation, you have an indicator, whether it comes from the trial or from the external data source. And then you have the treatment. I'll refer to it as the treatment indicator. As we said, treatment is equal to receipt under no non-adherence. So this, you can think of it as randomly assigned in the trial. And so some of the people get A1, random assignment of people get capital A0. And then we said we're going to work in the special case where everyone in the S0 data gets A equals 0. So one way you can think of an example of this is perhaps there is a well-established standard of care, call it A0. Then I'm doing an experimental study to evaluate a completely new treatment that is unavailable to anyone except in the context of my study. So that's A1. And so in my trial, I have A1 and A0. A0 being standard of care, but everyone outside my trial gets A0. It's not difficult at all to extend this to the case where there would be treatment variation in the S0, but I feel a lot of the nice and clean insights would be lost in more notation, so I'm going to avoid that as well, just in the interest of simplicity. We sometimes call this data structure a composite dataset. It's composite in the sense that it consists of two separately obtained datasets, the trial up top, and then the external data at the bottom. And whenever I use notation for sample size, I'm going to define little n as the sum of the sample size in the S1 and the S0, so N0 plus N1. And again, that's like the total length of my composite data set created by appending the trial with the external data. Okay, so again, going through the steps of the framework we went to at the beginning, I need now to introduce a causal model. There's not enough time for sure in this talk to do any detailed causal model definitions and introduction, but crudely at least, let me sketch it. I'm gonna use some kind of counterfactual, sometimes known as potential outcomes type model, where I'm gonna be freely referring to outcomes under hypothetical interventions to set treatment, possibly contrary to fact. And I'll expand my notation just a teeny bit to use Y, capital Y, superscript little a, to denote the outcome under intervention to set treatment, capital A to little a, again, possibly contrary to fact. And you can see I'm freely talking about setting treatment instead of setting treatment assignment, because for a second, we're working in a setup where there is perfect adherence. Now, to express one of my assumptions, it is useful to consider doubly indexed counterfactuals under joint interventions on both trial participation status, that's the little s, and treatment, that's the little a. And so I think of little s as all the outcome relevant trial actions other than treatment. And then I'm thinking of a as the randomized treatment. Little a is the randomized treatment. We're going to assume this away in a second, but it's an interesting kind of piece of notation that I didn't want to completely ignore. Okay, so what is my causal estimate? Again, going through the steps of the framework. I want to get the average treatment effect in the trial population. I think you'll give me that this is a very conventional kind of first pass treatment effect. I should say there is many interesting extensions of these ideas along the lines that Konstantin and Ravi were presenting in the previous section of the symposium to try to use these kinds of methods for conditional average treatment effects or for subgroup treatment effects. But let's start with the simpler estimate of the average treatment effect. And you'll notice I write this as the expectation of the difference of the two potential outcomes under treatment little a1 and little a0, but I take the expectation conditional on the population of the trial, capital S equal 1. And so again, this reflects my target population from the top, and that would be the primary interest, I think, for most trialists, or at least the first step in the analysis of any trial would be a population like the people in the trial. And then the last step is just linearity of expectation, to remind myself to say that sometimes all I have to think about is the potential outcome means, the expectations of each of the potential outcomes in the population of the trial. Since if I could get each of these, then I could get the average treatment effect. Okay, so nothing too groundbreaking in terms of my estimate, starting a little simple. Okay, so if this is my estimate, already I can see in the minds of the audience the question forming, why on earth do we need to use external data, right? Because in a simple randomized trial like I have here, like I will assume more formal in a second, association is causation. Now, I'm not saying association is always causation. I'm saying in a well-run trial with all the simplifications we made, no non-adherence, no loss to follow-up, no missing data, you can just look at the empirical difference between the arms, and that is a decent estimator of the average treatment effect we're interested, no external data needed. So just to say this a little more formally, the external data are not necessary for identification of my causal estimate, just from our basic intuitions about randomized trials. We could just use the trial. That's why we invested the money in running the trial and ignore the external data. So here my interest in using external information is just to improve the precision of my estimates. I want to just be more efficient in my analysis. And I think that's a critical thing to realize, because when we propose new methods for this kind of setting, we need to know that we are messing with something really nice. A clinical trial is a thing where inference is justified by the study design. If conducted and run well, no one should be able to mess too badly And so for me to come and say, let's use external data, I have to be pretty robust. I have to be careful not to rely on luck to avoid causing trouble in the analysis of the trial. And I will say the topic of bringing external data into trials, of course, has a huge history. I'm not the first one to think about this problem. But the methods that have been proposed since perhaps the 60s, probably even earlier, don't seem to be getting too much traction. And I think one reason for that is that many of the methods take risks that to a trialist may appear unnecessary. Many of the methods require a trade-off between bias and efficiency that perhaps to trialists is unacceptable. So just to tip my hand a little bit in terms of what I'll present, my goal is going to be to improve the efficiency, but without losing any of the robustness given to me by randomization. Now, to just make this a little more formal, we'll need to state some assumptions, and I'm going to discuss how each of these assumptions that I'll be stating are supported by the study design. So let me start by one that goes by the name of consistency in the causal inference world. It's an assumption that basically for units that receive capital A equal to little a, the potential outcome under treatment little a is precisely equal to the observed outcome of that unit. And so this looks almost like a tautology, but it's actually a pretty loaded kind of assumption. In the notation and the statement of this assumption are hidden requirements that the intervention is well defined, so that when I say big A equal little a, both outside and inside the trial, actually, I mean the same thing, and that there is no interference, so that I only have to think about a unit's treatment and not the treatment of other units in my population. And sometimes this is also referred to as a no hidden version of treatment assumption, meaning again, that there are no outcome relevant variations in treatment, so that when I say treatment is little a, 0 or 1, we can all understand the same thing and take the action and apply it to an individual. Now, this assumption is not entirely supported by study design, even in the trial alone, but it can certainly be strengthened by careful design. For instance, by having standardized treatment protocols, by choosing data sources appropriately, perhaps by not having too big of a clustering issue in the conduct of the trial, and so on and so forth. Okay, what's my second assumption? My second assumption is perhaps the nicest one, at least the top part of it, because I'm just going to assume the absence of confounding only in the randomized trial. So basically, the potential outcomes are independent of treatment. Here I make it given covariates. In most simple randomized trials, you get an even stronger assumption. But notice that I am only making this independence assumption conditional on S1. And so it only is needed at this step in the trial. Now, outside the trial, in our example, we said that everyone receives the same control treatment. And so this is just putting that in symbols. If I know S is 0, meaning if I know you're outside the trial, then I know your A is 0. Is this necessary? No, but it will simplify the exposition a little bit. And if this weren't true, then use of the external data is even more risky for reasons that I will explain. It's plenty risky even in this simple case. So that's why I think this is a good example. But if there is a possibility of treatment variation, just to be less cryptic, if there is treatment variation outside the trial, then this opens the window to the possibility of confounding outside the trial. And so this makes the external data even riskier to use together with the trial. Okay, now, as I said, the first one is given to us by randomization, this top part. The second part, I can do it by study design, by restricting my attention to external data where there was no variation in treatment. If such data doesn't exist, then this would be dropped entirely and we'd be doing an even riskier undertaking. Okay, then I need some kind of positivity condition. This one is entirely supported by the trial design, and it basically says that for all the patterns that I see in my trial, all the covariate patterns that I see in my trial, the probability of treatment is bounded away from 0. No one randomizes people with probability 0 to treatments you want to learn about. Most often you use half and half. So this is very nice. But notice that the probability of treatment A1 in the S0 data, in the external data, we assumed it to be 0 just over here. Okay. And so these three assumptions I feel are not super controversial. As far as it comes to the trial, basically I said there is positivity of treatment assignment given by randomization. There is no confounding in the trial. And as far as the trial is concerned, at least there is no, little a is a well-defined intervention. And so I have consistency. And I don't need to show a proof, I think, for this, but this is just a formal statement of what I mean when I say association is causation in the trial, because when I want the expectation of the potential outcome in the trial, then I can just also condition on the treatment that I want in the potential outcome. That's given to me by no confounding. And then I can use the consistency assumption so that if big A equal little a, then y little a equals y. And so this is the expectation of the outcome. That's the expectation of the observed outcome in the trial among individuals who received big A equal little a. And so that's a complete identification analysis, because the right-hand side is a quantity that is entirely involving observed data, y, and then you just look in the subset with S1 and big A equal little a. So we were successful in re-expressing the causal estimand, or a part of the causal estimand, since we need to do this for little a0 and little a1. We were successful in expressing it in terms of the observed data alone. And you can think of this as the population analog of the sample average in the arm with big A equal little a. Now, under the assumptions we made, and as is the case in many, many trials, you can also use the baseline covariates to improve your efficiency still without using external data. And this kind of relies in a slightly different identification result that says you can take the conditional expectation of the outcome given the covariates and then average that over the distribution of the covariates in the trial. I'm not going to talk too much about this, but it is an interesting result. Okay, now, up to here, I feel most of the things we assumed together are not super controversial. But let's take a glance at the things other people have on occasion assumed. So, for instance, in some of my work, I assume the absence of engagement effects. And so I say, as long as I know your treatment was little a, then I don't really need to know whether you received it in the context of the trial or in the context of the observational study. For people who like this terminology, this is an exclusion restriction assumption for the effect of trial participation on the outcome. And it essentially states that all impacts of trial participation flow through the randomized treatment. And so this is a formal way of saying there is no Hawthorne effects, there is no impact on participation on non-adherence. Of course, we already assumed non-adherence away, so it's not relevant here. And importantly, that there are no ancillary interventions in the trials that affect the outcome, not through the assigned treatment. Depending on your trial and your source of external data, this may be from very plausible to super implausible. And so I just wanted out there that a lot of work in the literature, including my own, by the way, invokes assumptions like this. The next assumption, again, I've used it many times. Many others have used it many times. Doctors use it informally a lot of the time, is some kind of assumption that at least conditional on covariates, that's the X, at least conditional on covariates, the expectation of the potential outcome can be transported from the S1 to the S0. And so this assumption is a strong assumption, and we'll discuss a little more whether it's testable or not in our setup. It's a strong assumption, but it is at the core of being able to use the external data in some way pooled with the trial data. And then the third extra assumption that people often invoke is some kind of positivity of participation. Basically, it's one attempt, one formalization of the idea that maybe I need to have sufficient overlap between my trial and my external data. And so I might say that for every covariate pattern, little x in the trial, I need the probability of being in the source data to be positive. Not everyone needs this, not every estimand needs this, but in a lot of work on transportability, something like this is being assumed. And long story short, my take is going to be that these three assumptions are risky, they're materially beyond what is justified by the trial design, and perhaps a trialist should be resistant to using methods that require these assumptions in a central way to ensure, for instance, unbiased estimation. Okay, so let me elaborate a little bit on this critique. So suppose I wanted to use these assumptions. It turns out that if that's the case, then the identification analysis I present here in abbreviated form allows me to pool the trial data and the external data for treatment A0. In particular, these assumptions taken together suggest that I don't have to only use the conditional expectation of the outcome given covariates in S1 and A0 and average it over S1, but instead I can have this combined pooled expectation over both S1 and S0. A naive way to use this kind of result is truly to pull the external data in the control arm of the trial and analyze it as just a bigger control arm. And I should say, I'm writing this over here, and I just gave a way of using it to guide estimation using regression. But there is also efficient, semi-parametric, doubly robust kind of estimation of this function. So it's possible, and papers have been written about it. But we have to ask ourselves, is it a good idea to use a result like this? And I think that's very risky, because if assumptions 4 through 6, and I would really be worried about the transportability assumption for sure, if they fail, then I will get the wrong result. And in fact, I'll get the wrong result. The bigger the external data is, the more wrong the answer I'll get, because the more external data I have, the more it will dominate the trial arm. And essentially, I'm using a non-randomized contrast, basically, of the trial arm with the external control data. So naively pooling, not a great idea, I think pretty obvious. The next thing is perhaps we could be a little smart and say, well, under the extra conditions I wrote, 4 to 6, there is an observed data implication. I'm not going to go through any kind of derivation of this, but it's kind of obvious even intuitively if the external data and the trial control arm are truly compatible between them, and compatibility is defined in terms of the assumptions I stated, then for every level of X in the common support of the two data sources, it has to be that the conditional expectation of the outcome, given that covariate pattern in S1 and A0, is equal to the conditional expectation of the outcome, given that covariate in the external data. And since this equality, which is an implication of the assumption stated before, does not involve any counterfactuals, this is just an equality to regression functions, it is testable in the observed data. You could use your favorite method of testing independence between the S1 A0 and the S0 group, given the covariates. This is a hard statistical problem, especially if you want to make fewer assumptions, but certainly there is a huge abundance of methods to test it. Now, the idea then would be to do this test, and if the test rejects, stop and use the trial data. If the test does not reject, then to use the combined data. I can't go too deeply into why this is known to be a bad idea, but basically, because you have this pretesting step, you can get bad finite sample performance, and you get very weird behavior, even asymptotically, of your estimators. So we're not going to do this, but just to conclude, given the risks of naive pooling, the risks of testing, and the risks of many similar methods that I can't really go into detail here, it would be nice to have a way to use the external data without taking too much risk. And so I'm going to sketch a way to do that. Okay. So the first part of my sketch is going to start by thinking about the trial-only estimator, just to fix ideas. And we call this maybe the augmented inverse probability weighting estimator in the trial. But what you need to remember about it is it only uses the trial data. It uses the propensity score. So for that reason, maybe we incorporate the knowledge that we have about the treatment assignment through the propensity score. And then it uses an outcome regression in this specific kind of structure. And then I can do this for little a1 and little a0. And then if I take the difference between the two, I have an estimator. I will call this one the trial-only estimator. It's basically an application of inverse probability weighting plus double robustness to the trial data. And since the trial data has known probability of treatment, this estimator, we can even, without thinking too much, conclude that it is robust in the sense that I can get the outcome regression model wrong, and this estimator will still be consistent. And under mild conditions, it will also have a normal distribution. But again, this estimator sees only the trial data. You can see because all my sums have SI, which is the indicator for the trial. So I zero out all the non-trial participants, and then it uses the regression model, which I estimate only in the trial because it's conditional on S1. So this is a trial-only, robust, if you will, estimator. So motivated by that, I can now define an entire class of estimators where all I did is I copied from the previous page, but I make the class dependent on some quantity over here where we had the propensity score before, and some quantity over here where we had the outcome regression before. And now I'm going to think about this class a little more abstractly. And many of the claims I'll make, I cannot really provide proofs, but there is a link to a very detailed paper by Richard Carlson and Guangbo Wang, myself, and others. And a lot of the technical details are fleshed out over there. And so, okay, so I have something where I had the propensity score. I feel since we're working with a trial, we can make our life easier and we can just use the true propensity score over here. And then we have this function, which note is a function of X, not necessarily obtained conditional on S1. And so we may call this class of estimators when this is equal to the propensity score, we may call it a class of randomization aware estimators. That's just my attempt to capture the idea that these estimators will have a certain kind of randomization supported robustness when this quantity is the true propensity score. Okay, so here's my plan of attack. I can make two estimators at least. The first one we already saw. It uses the true propensity score, and it uses only the trial data to learn the regression of the outcome. And so this is the estimator we saw just a couple of slides ago, which was the trial-only tau hat v hat estimator. Or perhaps, and that's my little contribution here, perhaps I can use the external data to learn the h of x function plus tricks to optimize that data for my trial. Okay, now what do I mean by tricks? This certainly needs many ugly formulas, so I'm just going to sketch it. But my trick is to notice that for any fixed function taking the place of h of x, call it h fixed of x, the estimators in the class are consistent, asymptotically normal, and have an asymptotic variance that I can write a formula for that depends on h fixed. Under the additional assumptions, the term in the asymptotic variance expression that depends on h fixed can be written just by algebraic manipulation using assumptions 4 through 6. Remember, these are the assumptions that we don't want to believe too much. So, but if these assumptions were true, I can write that term of the asymptotic variance in a way that is conditional on A0. So it uses the control group individuals in the trial and outside the trial, but is not conditional on S1. So this trick, if conditions 4 and 6 were true, would allow me to have a way of writing the asymptotic variance, the key term of that variance, in a way that combines the data. Notice that even if I'm wrong, even if conditions 4 through 6 do not hold, my estimator will remain consistent, asymptotically normal, and have asymptotic variance that I can write the structure of. So I don't, by assuming this, I'm not jeopardizing my asymptotic normality and consistency. Okay, so then since I can write that asymptotic variance, maybe I can search for the value of H such that that asymptotic variance is minimized when conditions 4 and 6 hold. And it turns out that for H of X functions in reasonable classes, and that certainly includes popular parametric models used in trials, this is a pretty standard optimization problem. And so we will call the resulting randomization-aware estimator, where I'm still using the true propensity score, but I'm plugging in H hat star, the efficient H star. We will call that one the randomization-aware, the optimized randomization-aware estimator. Okay, now, how am I going to do this? And there is links at the end that point to code. But the way I'm going to do it is I'm going to do all my analysis, my optimization for H of X, my solving for other terms that go into that asymptotic variance expression, my tau hat, my z hat, everything I'm going to do in one big M estimation stack. So I'm solving a collection of estimating equations. And the reason I do it is to simplify my life, and you get a estimator of tau hat z hat, the trial only estimator, and an estimator of tau hat H hat star, the optimized randomization aware estimator. I do this in a way that these two will be jointly asymptotically normal by standard M estimation results. You don't have to trust me. We hope to post the paper in a couple of weeks, but we can generalize this outside of the M estimation framework to general semi-parametric estimation. But it's just so much simpler to get the idea down if we're using more standard stuff. Okay, and so how am I going to estimate the variance-covariance matrix of these two things? I'm going to do it by the standard sandwich approach for stacked M estimation. So now we have a realization. Our realization should be that we have two imperfectly correlated. They're correlated because they use a lot of the same data, but not the identical data, asymptotically jointly normal and consistent estimators. What are they? The trial-only estimator and the optimized randomization-aware estimator. So I have two, and what happens is this one is great. Tau hat z hat is great because it doesn't need me to assume anything about the external data. This one is good because if I'm right and conditions 4 through 6 hold, it may be more efficient than this one by using the external data and using that optimization trick that we sketched. If I'm wrong and 4 through 6 do not hold, this estimator is definitely not going to be very efficient. It can be extremely noisy, but it's still going to be consistent because it belongs in the randomization aware class. And it's also going to be normal. And the joint normality I get from the M estimation. So when I look at two estimators, they're both consistent and asymptotically jointly normal. What if I combine them? And so the idea is to create a linear combination of these two estimators. Now, lambda, you can see, is the weight with which I'm doing the linear combination, lambda 1 minus lambda. And then I can study, this is an infeasible estimator, of course, because I don't know the optimal lambda to combine. But I can study the behavior of this expression on the right-hand side as a function of lambda. This is a problem that is really just a quadratic problem. Even medical doctors like me can do it. And it's also a problem that has been studied for a long time. And it turns out that we can get an expression for lambda star, which I call the lambda that minimizes the variance of this expression on the right-hand side. And that lambda star depends on the asymptotic variance of tau hat z hat, the asymptotic variance of tau hat H hat star, our two estimators, and it also their asymptotic covariance. But since I'm estimating everything just from before through M estimation, I am getting my computer to give me estimates of these asymptotic variances. And so I can do plug-in by putting hats over everything here, and that way I can get an estimate of the lambda star hat, which if I do, I will get a feasible combined estimator. Now, this estimator asymptotically has very good properties. Again, I won't show any proofs of this, but basically it's asymptotically normal. You can tell because it's a linear combination of two asymptotically normal, jointly normal things. And then it has asymptotic variance we can prove that is smaller than or equal to the variance of tau hat z hat or tau hat H hat star. What does this mean to me, the trial analyst? It means that my combined estimator, at least in large samples, is no worse than the best of the other two. And since both of them are robust, randomization aware, normal, and the combined one as well, I have this protection that I won't do worse than I would have done by ignoring the external data, but I can do a little better if I'm lucky. And something like conditions 4 through 6 is not exactly right, but perhaps approximately right. And so it's almost a free meal. It's almost free because it relies on large sample results. And so one way to test those large sample results is to do a simulation. So here, I won't give details on the data generating models. Again, code is linked at the end of the presentation, but we tried small trials, 50 people, larger trials, 200 people, and then just 200 external controls. And we had two scenarios. Scenario A, excuse me, is a benign scenario where all the conditions hold. Scenario B is a scenario where conditions 1 through 3 hold, the randomization ones, but everything else fails, and all the models are incorrect. So all regression models, except of course the probability of treatment, are incorrect. And for each scenario and for each trial size, we do 5,000 runs to get the usual measures of estimator performance. And just for comparison, we also have a trial-only estimator. We have naive pooling. We have test then pool only if the test doesn't reject. Then we have two newer ideas that go under the name selective and dynamic borrowing. And there's a lot of numbers on this slide, so I'll just run you through the big picture summary. In scenario A, where all the assumptions hold, no surprise, almost all the methods, at least when you get a large trial, large-ish trial, they have very little bias. I need to say for selective borrowing, we have quite a bit of instability in the small trial, so I wouldn't really believe these ginormous numbers. The people who propose selective borrowing have been very generous, helping us understand a little bit the inner workings of their packets. We did some tailoring, and so we can bring this down. There is still some bias, but it's certainly not this huge numerically unstable number that you see here. In scenario B, things are much more interesting in terms of bias, because the plain difference in means trial estimator does great. The AIPW trial only does okay. The optimization randomization aware estimator that we just saw together does good. And the combined estimator also does really well. You can see these biases are all near zero. But then the other methods, when the compatibility of the data it does not hold, appear to have not insignificant bias. That's particularly true for pooling, test and pool, and then for dynamic borrowing. Selective borrowing does reasonably well in terms of bias in our scenarios. Okay, now what happens in terms of variance? I won't discuss the results in too much detail, but our combined estimator is very competitive and usually in small trials appears to improve a little bit compared to either of the component estimators, and in general has better performance than the unadjusted analysis. The other estimators I'm not going to discuss too much because they have quite a bit of bias, except again, selective borrowing does decently well when the trial is large enough. And then I'll just say in terms of coverage, even in small samples, we seem to be doing pretty well, except perhaps a hint of undercoverage with small trials and really misspecified models and all the assumptions not holding. So this is something perhaps to worry a little bit about. But once you hit a little bigger sample size, coverage appears to be very good. And I'll just sketch this application. We took data from two trials, so no confounding in each one, but of course still some possibility of non-transportability. We're going to look at 6 weeks outcomes. These are schizophrenia trials. They have a common control placebo group, so we use that one as the external data for one of the trials. We call that one the index trial. We use the placebo arm of the other one as the external data, and we use a relatively small set of covariates, since with 100 people, perhaps one shouldn't be too aggressive. And the covariates we use were reasonably imbalanced between the two datasets, but fairly balanced within each of the trials. And here are our results. This is the AIPW estimator, the trial-only AIPW. You can see it agrees in terms of the average reasonably closely with the difference in means estimator, and it has much smaller standard error. That's perhaps a plug for using covariate adjustment in trials, even if you don't have external data. Then the optimized randomization-aware estimator gets a result very similar to the AIPW and the unadjusted, with a slight increase in standard error compared to the AIPW, and then our combined estimator, barely beats, is the same as the AIPW, and so this shows that you get to use you get the opportunity to use the external data for free, meaning you're not misled, you recover the efficient trial-only estimators results. And then you can see other methods can have large bias, including naive and pooling and test and pool. Dynamic borrowing does pretty badly. And again, in this dataset, selective borrowing appears to do similar to our method. So that's good news for selective borrowing, I guess. Code and data are available at the links. I'm sure the slides will be available so people can access them if they want. I will say we're working on a pretty major revision of the paper, and the code will be cleaned up. So if you have patience of a week or two, that would be great. You can go and download the best version. And the data, we don't own it, but currently, as far as I know, is still available, subject to approval by the repository. Okay, so just to summarize the contributions and hopefully have time for some questions. The big picture is to start with the research question and then select methods. I tried to do this in the trial augmentation space, and this is a very interesting, I think, and creative kind of space. Lots of people have many interesting ideas. We're certainly not the first, but there's this hope that the power of randomization and maybe rich external data can lead to advantages in efficiency with minimal or no extra assumptions. And with this, I'll stop. And thank you.
Thank you so much. And actually, we're at time, so how about we keep
Okay.
questions to the end?
Of course.
And we'll go to our next presenter.